similar to the one we described before. Of course, we're not going to ask many questions now, but so that at every int they pick, do that many, many times, and then they will pick a random subset of these qubits that they've transmitted, and they will test to see whether maybe Eve was present. So the way they do this is they play some kind of game, just the way that I described it before. Now, this time, they're going to ask themselves questions, so they're just going to flip a coin and determine on the outcome of this coin flip, they're going to, say, perform a certain measurement, which we can just label by 0 and 1. It's not very important what these are. And at the end, they can compare. And they can see how often they together were able to win the game. And there's a very peculiar property about entanglement, which is called monogamy of entanglement, which means that one person can never be maximally entangled the same way with two people. So in this case, suppose if we have Eve here, and the state would really be described this way, instead of what we really wanted, namely being in an EPR pair, this means that Alice and Bob will win the game less often, because their correlation, say their entanglement, is not as strong as if they would just have entanglement between the two of them, without Eve. Now, I'm not going to describe the details about this because I haven't introduced anything like operations on qubits or anything like this. But this is the basic idea about this. So if they detect later that maybe they expect to win this game in, say, 85% of the time. Now, if they see that over all these runs, we only achieved like about maybe, I don't know, 76%. Maybe this is, then they conclude that Eve is present and they abort. This is very similar to what I said at What the Heck, where they also detect that Eve's present in a completely different way. And then they also decided to abort if they detected an eavesdropper. So now if they don't detect an eavesdropper, if they really win 85% of the time, then they conclude that with high probability, they really share the remaining pairs will always also be entangled pairs of this form. And then they just measure and use that as a key. Okay. So in fact, only what I want to say is that the protocol that I described at What the Heck can actually also be phrased in the scenario. Okay. To summarize, as I already said last time, really, quantum computing really differs dramatically from classical computing, and one of the fundamental reasons for this is that entanglement really is different than classical correlations. By classical correlations, I now mean these cheat sheets that were there beforehand. And entanglement is really the most important, well, probably the most important thing in quantum computing, which really makes it happen, which makes it so much different from classical computing, and which really is responsible for the great speed up. And there's a lot of interesting questions. I mean, actually not so much is known, especially about if we have 3 players or more players, what's going on in these settings. Okay, this concludes my talk. Are there any questions?
In the GAH that game, you said that the 3 players win all the time, but later on you said that if there are 3 players, that it lessens the entanglement between 2 of them.
Ah, right.
I didn't get why.
Okay. Yeah, that's not entirely clear. I didn't say that. That's correct. That's a very good question. But they will play a different game in this case. So they don't play the same game. They will play a slightly different game. In this case, for example, they could play a game where they require that the product of their questions answers the sum of their outcomes. And in fact, they can play this particular game less well if there's going to be 3 of them and just 2 of them going to play this game.
Is there anything to stop Eve pretending to be Bob to Alice and pretending to be Alice to Bob? They might end up with different keys, but they could use that for the rest of the communication.
No. So what I have not actually said here, which I said in my talk at What the Heck, which is quite important, that even in quantum cryptography, actually Eve and Bob are assumed to start out with a very small amount of key. So you can really think of quantum cryptography as key expansion rather than key generation from scratch. And they will use this very small amount of key to authenticate their messages to each other. But the important part is that even if they start out with a very, very tiny amount, from this amount they can generate key till the end of time. Because they can use, so it has been shown that quantum cryptography can be what's called composed, which has the effect in this case that we can take some of the key which falls out of our key generation process and we'll use it as authentication keys for future rounds. Yeah, that's a very good question. Yeah.
Yeah. Some companies today claim to be selling quantum cryptography products. Yeah, I'm here. So some companies claim that they are selling quantum cryptography products today. So do you know if they're applying the principles that you've just described, or is it just marketing bullshit?
It's not marketing bullshit. They are actually doing what I told you in my talk at What the Heck. This is a view on quantum key distribution, which is mostly, say, if you phrase it in the entanglement picture, which is mostly useful to prove security of protocols. But no, I mean, it's not just bullshit. I mean, of course, in practical implementations, so this quantum key distribution has been proven secure in these beautiful pictures where we have these tamper-proof boxes basically at each end. But there have been some completely practical attacks where, for example, a device was not properly shielded and someone was able to shine a laser back into the quantum crypto device and just by the reflections figure out, for example, the alignment of the polarization filter inside this box. Of course, this is assumed to never happen in these ideal models, which are proven secure. So, but I mean, these boxes really do quantum cryptography. I mean, there might be some, say, practical problems, but I think they can be addressed. I think the most important practical problem really right now is that they cannot generate key fast enough. So what actually these boxes do is they don't do what I just said and generate a one-time pad. They will generate keys successively, smaller keys, and then use AES, for example, to encrypt the traffic using these keys. So it's far from ideal, that's true. Yeah. But yeah, I guess they're still working on it as well.